Yeah, so today we'll discuss about the mathematics behind the vehicle dynamics. So we'll discuss up to the steering, and in the next session we'll be doing the simulations on Adam software. So we'll begin. Okay, so in the first slide we have the comparison between the composition of the tires of two different vehicles. So on the right hand side you can see tire 2, which is like a truck tire. This is basically a heavy load vehicle tire, and this is of a lightweight vehicle tire. So you can see the composition, like the percentage of different components here. So you can see in the heavy load vehicles, we have a higher percentage of natural rubber and steel, whereas here we have lesser percentage of that. And if you compare the fillers, the percentage of that is almost the same in both the tires. So you can check here, like what do these components do? Like antioxidants prevent oxygen, anti-ozonates prevent ozone, and the curing system help in vulcanization, that is strengthening of the rubber. And then we have natural rubber. Then we have some synthetic polymers here, which affects the overall performance, and it is also impermeable. Then we have steel, which is also like a strengthening component, and we have fillers. So this is the basic composition here. You can compare the two tires. Okay, so in general, all materials are mainly classified into three types. So there are elastic materials, which are mainly showing the behavior of springs. Then we have metals, which is like a combination of springs and friction. And then we have a material which comes in between elastic materials and metals, which is called elastomers. These are also called as viscoelastic. This is nothing but a combination of springs and dashpot. Okay, so dashpot is like it's similar to friction itself, but friction is like a higher component compared to dashpot. So if this, you know what friction is, so I don't have to explain that. Dashpot works with viscous forces, so it is like similar to friction, but not exactly friction. So this is the elastomers. And these are the symbols, okay? So this represents a spring, this represents spring plus friction, and this represents spring and dashpot. These are like combined in parallel, and these are combined in series. Both of this will give an elastomer. So now we'll compare the graphs of elastic materials and viscoelastic. Like how are they different? So this is the graph of a typical elastic material, like you can say rubber. So what will happen is you have different regions here. You have elastic region, you have plastic region, and then you have the fracture point. So from A to B, whatever loading I give, it is always proportional. Okay, the stress is proportional to strain. So whatever loading I give, there is 100% probability that it will come back to its original state. So that is what elastic region means. And then you have plastic region where there is like some deformity, and then finally you have the fracture point where the material just breaks. So this is for elastic materials. And for viscoelastic, if you see, you have different graph for loading and unloading. And the area under this is nothing but hysteresis loss. Okay, here you don't see any loss. The energy is conserved, but here there is a energy loss. So that is what is meant by viscoelastic. It is not perfectly elastic and it is not perfectly rigid also. It comes in between. Okay, so now why are we studying materials here? So this is mainly we are studying the material of the tire. So in the tire, you know, there is loading and unloading. When the tire rotates, there will be both loading and unloading happening at the same time. So I told you that tires are made of rubber and like elastomer. So there is hysteresis loss, and this hysteresis loss is compensated by the engine of the vehicle. Okay, but since we are like dealing with engine here, it affects the fuel efficiency, and this is not favorable for us. So it is very important that we choose a better tire material and we have to maintain it. Okay, so here we have a stationary tire, which is like on the ground, and we can see the pressure distribution here. This is the contact area. So here the contact pressure is equal to the inflation pressure. That is, this is the contact pressure, which we are taking it as W. And we have the inflation pressure, which is the pressure of the air inside the tire. So those two are equal. And this is the distribution, which is like a parabola shaped. But what happens when the tire is rotating or it's moving? Okay, it's rotating in anti-clockwise direction. So since it's rotating like this, we say that it is getting loaded here and it is unloading here. So this distribution, right, which was like this, will get shifted like this. So this contact pressure, which was acting at the center, will get shifted here. So now what we try to do is we try to balance it. So we try to get this to the original position here. So when we do that, we can't just put it like that. We have to put a counter acting force here so that these two will cancel and we'll be remaining with the old W. So now what we do is we keep this as it is and we take these two forces and we can see that it will act as a couple here, which is like M, and this is a moment which is acting in the clockwise direction. Okay, so since the wheel is rotating in the in anti-clockwise direction, we take a rolling resistance which is acting opposite to the motion. Okay, so this is the direction of rolling resistance. This is traction. Traction is a force which keeps the tire bound to the ground. So this is acting along the direction of the rotation of the wheel. So these are all the forces acting on the wheel. So now I told you about rolling resistance. It is not exactly friction. It comes from the property of elastomers, that is the tire material, which is viscoelasticity. And the formula for FR is small fr into W. Okay, W is I told you it's a contact pressure. And small fr is nothing but the coefficient of rolling resistance. Okay, so now we'll be studying the weight distribution on the front and rear tires. This is very important part of vehicle dynamics. This is like a car and we'll be learning the three axes. The x-axis is called longitudinal direction, y is called lateral direction, and z is called vertical direction. So we are considering the car to move in a inclined road, which is inclined at an angle of theta. So the car is moving upwards. So here we have the different forces. So this is WF, which is weight transferred on the front wheel. WR, which is weight transferred on the rear wheel. This is the center of gravity. We have W acting downward here. And we take H as the distance of the center of gravity from the road. So this is H. RF and RR are the rolling resistance, which is acting opposite. The car is moving this direction. This is acting opposite. This is on the front wheel, so RF. This is on the rear wheel, so RR. Uh, RA is the aerodynamic force, which is acting at a distance of HA from the ground. FT is called dragging force. So this comes into count when the car is pulling something behind it. Okay, it can be anything. Otherwise, most of the time this is ignored. Then you have L, which is like the center to center distance. The center to center distance of the wheels. Okay, it's from the center of this wheel to the center of this wheel. That is the distance L. So this will be L1, which is the distance from the center of the front wheel to the center of gravity, and L2 will be the other. So we'll resolve this W force into W cos theta and W sin theta, and we'll apply another force which is called the inertia force, which is in the opposite direction to the acceleration. So we have made some basic assumptions here. We are taking theta to be very small, the inclination of the road. So cos theta is equal to 1. R is nothing but the rolling resistance is equal to, I have told you this formula in the previous slide. So FR into W. And here we also consider that this distance is equal to HA and HD. So these are the three assumptions we make here. Now we'll be like solving basic equations. So first one is like all the forces on the car are like balanced. So here you see W by G into A is equal to uh, FF plus FR, so which is acting in this direction, minus RA, all that. You can just like apply this formula on this. You can just balance out the forces in the X direction. Then you'll finally get this equation here. So here I told you F and FR represents traction. RA is the aerodynamic force. Capital R is the rolling resistance, which is nothing but RF plus RR. And FT is the dragging force, which in many conditions we'll consider it to be 0. Then we'll take moment about A, moment about this tire. Again, you can just solve these equations. Like moment about this will be WF into the perpendicular distance here, which is L, plus RA into H. RA is here and perpendicular distance from A will be HA. So you can again apply this equation. It means that moment at point A is 0. So you can just calculate the moments of all other forces here uh, at point A. So rearranging this equation, you'll find out what is WF. Similarly, moment about B axis you can find out, and you'll get WR. So you'll get WF and WR, which is the weight transferred to the front wheel and weight transferred to the rear wheels. So solving all these equations, equation 1, equation 2, equation 3, you'll get these two values, which is WF and WR. This is very important. It will tell you what weight is falling on the front wheel and what weight is taken by the rear wheels. Okay, and we consider that the total traction force is equal to FR plus FF, and the total rolling resistance is equal to RF plus RR, which is equal to FR into W. This is the formula which I gave you in the first, which is like the rolling resistance formula. So capital F is the tractive force, and this is limited by the power and ability of the tire to take the load. So these two are the main things that decide the tractive force. So that we saw when the car was accelerating on the road, on an inclined road. So now we'll see what happens during braking. So actually, like you can expect while looking at it itself. So there, what we do, everything is the same, like compared to the previous diagram. Only one difference is that their inertia force was acting in this direction. Now, since it is braking, it will be acting in the opposite direction. Rest everything will be the same. You can refer to the previous slides and calculate the formulas. Ultimately, you have to find out just WF and WR, like what weight is acting on the front wheel and what weight is acting on the rear wheels. Okay, so now we come to the concept of locking of tires. So in braking, right, you can do three things. First thing is you can lock the front wheels only. Second thing is you can lock only the rear wheels, and third thing you can lock both the wheels at the same time. So we'll just see what happens if you lock the rear wheels first. So first of all, when you're locking the wheels, right, uh, the car will not go in a straight line. Okay, it will start experiencing a force which is like a centrifugal force. This is mainly because of the road camber, the road bumps, and the wind. So this thing, right, it shifts the car from the straight line motion to inclined motion. So now, since the rear wheels are locked, there will be no force acting from them. So the front wheels will try to oppose this force by giving a counteractive force. So this force will start acting here. Now what will happen is the car will move in the direction of this force. So now what will happen is the front wheels will also start giving the braking force. Okay, so this FPF is nothing but braking force because of the front wheels. Now if you see, right, this is the line passing through the center of gravity of the car. So this force will try to rotate the car about that axis. So now what is happening is the car is getting rotated like this. So this is the front part of the car. Since it's getting rotated like this, the front part of the car will come here. So you can see that the car is rotated by 180 degree. The car was going like this, it's going like this now. So this is what happens when you lock the rear wheels first. So you can see how dangerous this is. But now we'll see what happens in front wheel locks. So this is the car, and here again the centrifugal force acts, and here the front wheels are locked, so the rear wheels will try to oppose it by producing a force in this direction. Again, there is a braking force here because of the rear wheels, which will try to push the car in the straight line path. So you can see that the car was trying to move away from straight line, but this force is trying to get it back to the straight line. So compared to rear wheel locks and front wheel locks, we can actually like see how front wheel locks are much better than this, because this is trying to rotate the car by 180 degrees, and this is trying to get it back to the straight path. But one thing is, front wheel locks are also not preferable because they will try to have an impact on the steering capacity. So the best preferred thing is like you lock both of them together, like front wheel and rear wheels together. So now we'll see the maximum deceleration that happens during braking. So we'll consider a car which is like moving on a straight road without any inclination. So since it's braking, I told you the inertia force will be acting in the front direction. This is L1, L2, L. This is rolling resistance because of front wheels. This is rear wheels. This is the braking force. Okay, in case of acceleration, it will be traction force. In case of braking, it will be braking force. So this is braking force because of the front wheel, and this is braking force because of the rear wheel, and this is height of the center of gravity from the ground. So here, now what we do is we try to balance the forces. So FPF plus FPR plus RF plus RR, since all are acting in the same direction, is equal to this force. So we rearrange it here, and you get this. And then what we do is here we try to substitute the value for R. RF plus RR is nothing but capital R. And for capital R, we can just put this value. So you'll get this equation here. These two equations come from the previous slides where we solved the weight distribution. So you can take those equations from there. Now what I'm trying to do is I'm trying to substitute this into this. Okay, so I get WF and WR here. Uh, Now from equation 1 here, you'll get FP, again rearrange, FP is here. So this is here, you take FR into W on the opposite side. There's one more relation here, that braking force is equal to some constant KBF into the total braking force, okay? And for rear wheels, it will be KBR into total braking force. So that is a relation here. So we'll substitute this here and you'll get this. So finally, you have that for locking for front wheels, this is the d by g value. That is this is the maximum deceleration when front wheel locks, and this is for the rear wheel locks. So this is the formulas we got from the previous slide, d by g for F and d by g for R. I have considered that FP, that is the total braking force, is the sum of front wheels and rear wheels. And I told you this, that braking force for the front wheels is equal to some constant KBF into the total braking force, and this is similar for the rear wheels too. And there's one more relation, that KBF plus KBR is equal to 1. Okay, so these are some conditions you need to remember. So I've solved these equations for a car assuming some data. So we have h value, like the distance from the ground to the center of gravity, as 1 meter. L1 as 3 meter, L2 as 1 meter, and L is nothing but L1 plus L2, which is 3 plus 1, 4 meter. And I've taken mu to be 0.6 and FR to be 0.2. After substituting all the values into this, I get a relation like DG and KBF. Here, D by G and KBF. Here also it is like D by G and KBF. So I can plot a graph here to get a relation for both front wheels and rear wheels. So if I try to plot the graph, this is how the graphs will look. It is D by G versus KBF graph. So here, if you see, right, the two graphs will intersect at one point. So here the d by g value is 0.8. You can see here d by g value. So take g on the other side. So d is equal to 0.8 g. And kbf value for that acceleration is 0.45. kbr value you can just find out by doing 1 minus 0.45, which is 0.55. So here you'll get these values, the point of intersection. Now if I want to check on the either sides of the two graphs. So if I check here, this side, you can check that d by g for R, that is rear, is greater than for front wheels. But you can see that for this side of the graph, KBF is greater. Since KBF is greater, I am telling that front wheels will lock first. Okay. Since d by g R on this side of the graph, for rear wheel, you can see if I take a line passing here, d by g for R is greater than d by g for F. Since KBF is greater here, we'll tell that front wheels will lock first. And if I try to check this part of the graph, it will be the opposite. Okay, here front wheels come first. So d by g for F is greater than d by g for R. So here rear wheel should lock first. And point of intersection is where both are equal, and here both the wheels lock together. So now we'll discuss about the minimum stopping distance while braking. So once you brake, after what is the minimum stopping distance? So this we'll try to calculate. So the mass of the car is taken to be W by G in general, but we'll multiply it by some constant which is called gamma B. So gamma B is nothing but equivalent mass factor, taking into account the mass moments of inertia of the rotating components involved during braking. So this is a external factor which would be multiplying it with W by G. So I hope you know this formula. Acceleration is equal to V into dV by ds. This is the most basic kinematic equation. Now I'll take this ds on this side. A into ds is equal to V into dV. A is equal to, okay, this equation has come from the previous slides where in the diagram, right, you'll see the inertia force which has acceleration, and from there you'll get this equation. Even sigma r will come from the previous slides where it is just you're balancing the forces and you'll find out this. Now this thing that is aerodynamic forces, we never discussed about this. So this is like a theoretical formula. Uh, it's like CD into A into V square into rho by 2. Okay, CD is a drag coefficient, A is the projected area, V is velocity, rho is density. So this is the formula. If you see this, right, CD, A and rho are constants and even 2. So you can take this together and just put it as CA. We are trying to find the relation between RA and velocity. Okay, so RA is equal to CA into V square. We can see that RA depends on velocity as square. So I'm trying to put RA value into this. So I'll substitute it here. Now I want to calculate the stopping distance. So I need ds here. So what I'm trying to do is I'm trying to rearrange this equation. So I'll get uh, v into dv by a, and then a I have, which is this, which is nothing but fb plus sigma r, which I found from here. So substituting all of that and integrating it from v2 to v1, I'll get the stopping distance. Yeah, so this is the stopping distance after integration, you will get it this. One more thing you have to keep in mind is that braking efficiency, that is NB, uh, we have like in the previous derivation, you have considered it to be 100%, but usually it is always less than 100%. So we have to take that in mind, and the formula will get modified to this. So this is a final formula which we'll be using to calculate the stopping distance. But one more thing is like it should be pointed out that in practice there is a time lag between the application of brakes and full development of the braking force. So this time lag depends on the response of the brake system. So usually there will be a time lag. So we'll be considering that as SA is equal to TD into V1. So TD is the response time, which is nothing but the time lag, and V1 is the initial velocity. Okay, so now we come to the slip angle. uh, I discussed about one thing, that is in the locking of the wheels, that because of the centrifugal force, the the wheels which is not locked, like the wheels which are still rotating, will try to produce a force counteractive to that. So that is nothing but called as the lateral force. So here you'll see that this is the wheel, this is the weight, and here that's the centrifugal force which it experiences because it is trying to rotate in this direction. So here there will be a counteractive force, which is Fi, which is nothing but lateral force. And this Fi is given as mu y into W. So if you see the diagram, right, this is like the side view. Uh, so you have Fc here and Fi here. But if you see the tire, right, there is already a force which is acting in this direction, in the motion of the wheel. This is the centrifugal force. This is the force experienced by the tire. So we are not interested in this. We are interested in the forces exerted by the tire. So these are the two forces. Here, if you see, Fi is acting at a distance called A, which is called pneumatic trial from the center of gravity. So because of these two forces, if you usually see, right, if you have two forces like this, the resultant will be in this direction. But here, what will happen is you have this kind of variation. Okay, because of Fy and Fx, you'll have this kind of variation here. So you'll see that this is the variation of the forces because of these two. And then the tire will try to move in this direction, okay, because of this. And the angle which is actual motion and the tendency of the tire to move, the angle between those two is called alpha, which is nothing but slip angle. So this is a slip angle. You can see it's the angle between the rolling wheel's actual direction of travel and the direction towards which it is pointing. So here what happens is, yeah, this is the tire pointing direction and this is the actual direction, because of these two forces, this is the direction. So now I told you that this force is not acting exactly at the center, it is acting at a distance of A. So this is a line passing through the center of gravity. So this force will try to produce a torque in this direction. Okay, it is called mz, which is nothing but the self-aligning torque. It will try to align the tire in the original position. So this is mz. So now we'll try to find out the relation between this slip angle and the steering angle. Okay, so we'll be using the bicycle model. So we'll consider this to be a bicycle. So this is the front wheel and this is the rear wheel. Again, like this is the distance from, and this is the center of gravity. So this is A, distance from center of gravity to front wheel, and this is B. And now what I'm doing is I'm trying to rotate the front wheel. This is the steering angle, okay, which is delta. I'm trying to rotate the front wheel in this direction through an angle of delta. So now what will happen is slip angle and lateral force is acting here. In case of P, this is the lateral force and this is the slip angle. Okay, here at the center of gravity, there is omega, which is nothing but the yaw angular velocity. Okay, this is omega, and here u is nothing but the forward velocity. V is nothing but the vertical velocity, and beta is the steering angle at the slip angle at the center of gravity. So these are all the terms we used here, and r is the radius of the curve the bicycle is trying to take. So here we'll try in this triangle we can use tan beta, which is like opposite by adjacent, which is v by u. Since it is all, we are considering all the angles to be small angles, we can approximate it to beta is equal to v by u. Now we'll check at point B. Here because of this, right, omega, when if we try to calculate the here on at point B, because of omega there will be a component acting in this direction. Okay, this is like when it comes here it will be like this, which is like b into omega, and here this vertical velocity acting here as well and the horizontal velocity here. So at point B, tan of alpha r is equal to, here opposite will be nothing but b omega minus v. Okay, this minus this will be here divided by u. So this is at point B, and then at point A it will be here we have delta and here we have alpha f. So it will be delta minus alpha f, and then we have similar, we have put the components here. So it will be a omega plus v divided by u. So this is for point A. Then here you can just substitute that we have taken u to be r into omega. So we can substitute this, and finally we'll find the relation between steering angle and the slip angles. Okay, L is nothing but a plus b. Okay, that is L, and r is the radius. So this is the relation between the steering angle and the slip angle. Okay, now we have the understeer and oversteer. So same bicycle model, we'll try to balance the forces. So here what we do is we consider all the angles to be very small. So I can take this f by f to be in the vertical direction itself. So f by f plus f by r is equal to this force, which is the centrifugal force, mu square by r. So I have balanced the forces here. A plus b is equal to L, which is nothing but the length of the wheelbase. Taking moment about B and taking moment about A, you can solve these three equations here again. And one more thing is that this I have already told that Fy is equal to Ca, which is nothing but cornering stiffness into slip angle. This is one more relation here. So we can find it out for Fyf and Fyr. So we can substitute this here. And then I have this formula which I got from the previous, the relation between steering angle and the slip angle. So I'll substitute this here, everything. And then finally I'll like modify it and I'll get this equation. So this is the equation we got from the previous slide. So there are different cases. Okay, one thing is where this B into CAR is equal to A into CAR. So when these are equal, this whole term will go off and I'll be left with delta equal to L by R. So this tells that at any speed of the car for same turning radius, we have to give same steering input. Okay, so how much of the, like how much turn you're taking, similar like steering input you're supposed to give. Now we have the understeer condition where B into CAR is greater than C into CAF. So here delta will be equal to, we are taking this whole term to be K1 into U square by R plus L by R. So we are, when we see for this condition, right, K1 will be greater than 0. For this condition, K1 was 0. For this condition, K1 will be greater than 0. So this will be the understeer condition. For case 3, we are considering the opposite, where A into CAF is greater than B into CAR. So here in this case, K1 will be less than 0. So this will be the oversteer condition. So here you can check the graph. This is the case 1. This is the case 2, which is the understeer. And this is the case 3, which is the oversteer. I hope you know what understeer and oversteer is. Like understeer is like when you're trying to turn the car by a certain steering angle, the car won't be able to turn it like turn properly. And oversteer is like it's trying to oversteer, like the car will turn more compared to what input you have given. So one point where you have to see in this graph is at here, like you can see point x1 where delta will become 0. This delta will be 0, and so here what happens is this is the oversteer graph. So here this point, right, you do not want any wheel input at all. Like no steering wheel input is required for turning at this point. Okay, and the velocity at this point is called as the critical velocity. So now we'll be learning about the Ackermann steering geometry and the anti-Ackermann steering geometry. So this is how the geometry looks like. So here if you see the wheels, right, the inner wheel is turning at an angle greater than the outer wheel. So you can see here, this is more inclined than this. And if you try to join, right, they are where they intersect. So there will be a common point and they are trying to rotate about that common point. But in anti-Ackermann, it's the opposite. So the outer wheel is trying to is rotating at a greater angle compared to the inner wheel. And if you try to check their common point, there's no common point here. Okay, this one is rotating at some other axis and this one is rotating at some other point. So that is anti-Ackermann geometry. Okay, so there's one thing that when a car moves, right, when it's turning, the force on the outer side is greater and the force on the inner side is less. So there's one more thing that if the force increases or the loading increases, the slip angle increases. So they are directly proportional. So this is the graph for the lateral force versus the slip angle. So I am just increasing the force from 100 to 200, 200 to 300, and I'm trying to compare. So I'll just try to increase the slip angle here. So alpha 1 to alpha 3. So here what happens is this is the outer tire and this is the inner tire. This is the steering angle delta and this is the slip angle alpha 1. This is the direction of travel. Here what happens is the direction of travel, since the loading is increased, okay, the load is increased, so the slip angle will increase. Okay, here it was alpha 1, here it increases to alpha 3. You can see here as the loading increases, slip angle increases, so here it increases. So now what happens is the direction of travel is here, but here it has got shifted this side. If I want to check the original direction of travel, it will come somewhere here. So for that to happen, what will happen is the inner tire will be uh, tilted more, okay, towards inward. So you can see that the sorry, the outer tire will be tilted more compared to the inner tire. So you can see here, this is the anti-Ackermann geometry. But for the other case, it's the opposite, where here you'll again try to check if the loading decreases, the slip angle decreases. So here you'll check this is the inner tire and this is the outer tire. So you'll be looking at the opposite way. So here the slip angle is greater, here the slip angle decreases. So in that case, we'll be having the Ackermann geometry. Uh, yeah, so this is it for today's session. So we have discussed all the mathematics involved in vehicle dynamics and especially the steering system. So in the next session, we'll try to simulate all of this on Adam software.